Hello, class. Okay, so this is an important topic, so I want to kind of have a separate video just to talk about this Equipartition Theorem. And before we even state what it is, I want to talk about the internal energy of a gas. So a gas, it's made out of molecules, could be made out of individual atoms. Like if you have helium, helium doesn't bind to anything. So if you ever get, like say you go buy one of those canisters of helium to fill up balloons or something, you can get those at party stores. Yeah, that's just helium in there that are just individual atoms floating around. By the way, those things, kind of surprised they actually sell that stuff. Helium is kind of rare, and because it doesn't react to anything chemically, that when you release it to the atmosphere, it's essentially gone. It's just going to remain helium. So we'll have trace amounts of helium, which we'll never be able to recover. And, you know, the only reason we have any helium on Earth, really, is because of radioactive decay. Like when uranium decays, for instance, it gives off helium. And so it was originally discovered on Earth anyways. It was actually discovered in mines where they're digging uranium. They found this helium gas. I said when it was originally discovered on Earth, actually helium was first discovered in the sun. Later they found that it existed on Earth as well. But anyways, yeah, it's a very finite supply of helium and basically impossible to recover once it's used if it's released into the environment. So yeah, and it's very important gas as well. It's used in like MRI machines in a lot of industries. But, sidetracked here. So yeah, like a helium gas, that's just individual atoms floating around. That's what we call a monatomic gas. So that's just, atoms bouncing around. Now, another type of gas is diatomic. So mono 1, dia 2. So here we have, like, say, helium. Now, diatomic would be hydrogen, for instance. Where you have a hydrogen, and they're bound together by this electrical interaction between the two atoms. And these gases can behave differently. If we look in terms of energy, what types of energy can this monatomic gas like helium have? It has kinetic energy. And actually I'll leave a little space there. So the kinetic energy we'd have 1/2 times the mass of the atom in this case, times the velocity squared, which has 3 components. So for kinetic energy, it would look like this. We could expand this 1/2 mvx squared plus 1/2 mvy squared, 1/2 mvz squared. Now, if we look at a diatomic, here we have kinetic energy here. If we look at a diatomic molecule, it can have kinetic energy as well. It's going to have kinetic energy. You know, the spacing here, you can treat it almost as a single, object. And, it's moving around. But it can also have rotational energy. Now, in general, rotational energy, remember if an object's rotating like 1/2 I omega squared. However, I can write down a basic formula. Here we have, I'm going to call this KT for translational kinetic energy. Now, generally for rotational kinetic energy, basically you have 1/2 I omega squared, but when we have a coordinate system, like an x, y, z coordinate system, it doesn't have to be rotating in like the x or the y, like about the x, y, or z axis. In general, the axis of rotation is going to have components. It'll be pointing, it'll have like x, y, and z components. So we can write this now. This would be in general for like a three-dimensional object that's rotating, where these are the moments of inertia about each axis, and omega, these are the angular velocities about each axis. Now let's look at a diatomic molecule. Let's say that this is the x direction, and that's the y direction, and the z direction is coming out of the board. Now the moment of inertia in the x direction is going to be just about 0. If you look at it, you have like one particle at the end here. It's rotating about this axis. Compared to Iy and Iz, this is essentially going to be 0. Remember, the moment of inertia, it depends on the mass and how far the mass is from the axis of rotation. So if this is the x direction and it's rotating about that axis, the masses are basically at the axis of rotation. And so if they're point particles, this will be exactly 0. But if these atoms are a little extended in space, this won't be 0, but close enough to it. Compared to, like, say there's a mass at the end of each. If it's rotating this way, that's nothing compared to rotating this way or rotating this way, like about the y or z axes. And so, basically, let's cross this one off. So for rotational kinetic energy, we have two terms. We'd have 1/2 Iy omega y squared plus 1/2 Iz omega z squared. And, if you look at velocity, mathematically they're very similar. They're both quadratic in this variable. They're like the mass and these moments of inertia. They're fixed, but, these velocities are going to determine how much energy it has. And it's quadratic in these variables, all these terms so far. Now, there's another type of energy that this diatomic object molecule can have, and that is vibrational. Now, there's a reaction between, an electrical interaction between these two atoms. And we can treat it kind of like a spring force. Even though it's nothing like an actual spring, but that spring force is actually a good model for a great number of things. Particularly for like small vibrations. Yeah, it's a good model for a great number of things, just to treat it like a spring. There's reasons for that. Basically, if you expand the energy in like a Taylor series, the first term that you would keep is this quadratic one, which would be like the spring force, 1/2 kx squared. And then there's an x cubed term and an x to the 4th power term, but those are much, much smaller. So a lot of physical systems, if you just keep like that first approximation, that quadratic term, then the spring force is a very good representation of what's happening here. And so remember, it has kinetic energy because it's like moving. And if it's vibrating, the molecules are also going to be moving back and forth, or the atoms are going to be moving around. So they're going to have translational kinetic energy in addition to the overall motion of the molecule. So there's going to be this like spring force like interaction. So we're going to have say 1/2 kx squared, where k is like the effective spring constant. And then we're going to have some kind of kinetic energy for the motion of the individual atoms. And so we have two of these quadratic factors. And basically, so for a diatomic molecule, we should expect all of these. We'll just call it V. So we have translational kinetic, rotational kinetic, and then vibrational energy, which contains potential and kinetic energy. So the energy of the gas, it's going to have like all these factors that apply. For a monatomic gas, nothing but translational kinetic energy. For a diatomic gas, it's going to look like this. Now, let's say we look at something more complicated, like a water molecule. We have like H2O. Now, this, writing down the energy for this would be, significantly more complicated because there's different types. Well, this can have all three rotational terms. We wouldn't cross this off for something more complicated than a diatomic molecule. For this one, we would have, it can rotate about any axis. The moments of inertia are not going to be zero about any of these axes. And, yeah, we can have different types of vibrations as well. We're not going to get too much into these more complicated molecules. But the idea is, we want to kind of count the number of these quadratic terms that show up in the energy. If we just write down the energy, taking every term into account, we call each of these quadratic factors a degree of freedom. So for a monatomic gas, I'll just write down the number of degrees of freedom. Say we have 3. The kinetic energy, we'd have 3 terms. So 3 degrees of freedom, and that's it. Now, for a diatomic molecule, we'd have 3 for kinetic. That one's gone for diatomic, so we have 2 more for rotational. And then vibrational, we have 2 more terms. So this would have 7 degrees of freedom. And water, we're not going to get into more complicated molecules. You kind of mention them, but we're not going to get into details with those. We're only just going to focus on monatomic and diatomic gases. All right. So, now, the title, Equipartition Theorem, what the Equipartition Theorem says is that each degree of freedom contributes an amount 1/2 kT towards the energy of the system. So before we were looking at this molecule, we found that the average kinetic energy was 3/2 kT. Well, yeah, we're just talking about the translational kinetic energy. It has 3 degrees of freedom there, so this is just an example of this equipartition theorem, what we did before. But the equipartition theorem is much more general than that. So if we look at, for a monatomic gas, here, let's do this. The energy all right, so, yeah, for a monatomic gas, we have 3/2, the 3 degrees of freedom, and that's it. So the total internal energy would be 3/2 kT. That's for each molecule. So we can write this as 3/2 N kT. So that would be the internal energy for a monatomic gas. It's just the kinetic energy. But if we look at a diatomic gas, there's 7 degrees of freedom. So we should expect this to have 7 halves. kT. So this is mono. And this is diatomic gas. So this is what we should expect for the internal energy of a gas. It depends a lot on what type of gas it is. Pretty significant difference between monatomic and diatomic gases. Now, of course, we did not prove this equipartition theorem. This is something that comes from statistical mechanics. That'd be another course entirely. But this is actually based on Newtonian mechanics, and that's going to be an important point later on. Like what we're doing is based on Newtonian mechanics. Okay, so that's the equipartition theorem. You kind of have to look at the number of degrees of freedom, and that'll tell you what the internal energy of a gas is. And a very important point is the internal energy of a gas only depends on the temperature. Like for any particular gas. Like if you have, say, nitrogen gas, that'd be N2. They'd form, bonds. That'd be a diatomic gas. So we'd expect the energy, based on what we've been doing so far, to be 7 halves NKT. And it's nice to have an expression. Like, for that particular gas, we can see the internal energy only depends on the temperature. That's a very important point. So, kind of a shorter video, but this is a very important topic that deserves its own, its own video. So, I'm going to stop here, and next we're going to talk about the specific heat of a gas.